Title: Infantile Amnesia, Evolution's Strangest Feature. This is the reason you cannot remember being a baby, and the strange possibility that forgetting those years was one of the smartest moves your brain ever pulled off. Every single person who has ever lived went through years of intense experience. They can no longer reach, and scientists have started to suspect that blank stretch was never a flaw at all, but something evolution built on purpose. The phenomenon carries a name. Researchers call it infantile amnesia, and it describes the missing autobiographical memory covering infancy and early childhood. They also define it a second way, as the much faster rate of forgetting that runs through the young compared to grown adults. Either definition lands you in the same place, which is the first few years of life that have gone almost completely dark. Here is where it gets odd. Young children happen to be relentless learning machines. Inside those early years, a child learns to walk, learns to read faces, absorbs an entire language from nothing, and figures out a whole world stuffed with objects and people. That capacity to soak things up is staggering, and yet the grown version of that same child keeps almost none of it. That contradiction sits at the center of everything, and it explains why scientists reach for a specific word when they talk about infantile amnesia, and that word is paradox. Unraveling the paradox starts with a question that sounds almost too simple to bother asking. Do babies build memories at all? For a long stretch, the comfortable answer held that infants simply cannot record memories the way older kids and adults do. That comfortable answer collapsed under testing. The researcher who helped topple it went by the name Carolyn Rove Collier, and her tool was a mobile, the kind that dangles above a crib. She ran a ribbon from the mobile down to a baby's foot, so a single kick set the whole toy dancing. Babies adore this. They catch on fast that kicking makes the toy move, and the kicking picks up. And that little burst of learning is exactly what she wanted to measure. The real test arrived later, when she checked whether the babies still held the trick. Infants as young as 2 months hung on to that foot kick technique for 1 to 3 days. Push the age up to 6 months, and the memory of the correct action stretched to 15 or 16 days whenever a reminder nudged it awake. That finding rearranged the entire question. Babies plainly do form memories, and they keep them, at least for a window of days, which meant infantile amnesia was never a failure to learn in the first place. Something happens to these memories after they form, and whatever it is, it works quickly, wiping them out at a startling pace. The idea itself has aged past a full century, and it traces back to Sigmund Freud. Writing in 1905, inside his work, 3 Essays on the Theory of Sexuality, Freud gave infantile amnesia its name. He kept noticing the same wall whenever he asked patients for their earliest memories. A blank curtain drawn across the opening of a life. Freud reached for an explanation, and it was about as Freudian as they come. Those early memories, he argued, sat perfectly preserved but locked away, actively repressed because their emotional and sexual charge made them too hot to hold. Freud missed on 2 counts. Decades of normative studies have turned up no evidence at all for the repression model, and that explanation has quietly been retired. His timing was off too. Freud claimed the amnesia stretched deep into the 6th or even the 8th year of childhood, which reaches far past the real boundary. So where does that boundary actually fall? Ask a room full of adults for a single earliest memory, and the grand average across many studies settles right around 3.5 years old. Most first memories cluster between 3 and 4, and almost nobody carries a real memory from before the age of 2. The fog also lifts gradually rather than all at once. Recollections thicken from roughly 3.5 up to 7. And only by about 7 does a person finally own the adult-sized spread of autobiographical memory. This is exactly why 2 grown siblings can stand in the same childhood kitchen while one draws a total blank, and the other replays a birthday because the offset of childhood amnesia behaves like a slope, never a clean wall, that gives us the shape of the thing. The harder question comes next. What is physically happening inside the skull? To scrub these years away? Here the story slips out of psychology and into neuroscience, and this is where it turns genuinely surprising. The front-running explanation zeroes in on one brain region, paired with one deeply counterintuitive process. The region is the hippocampus, the structure that sits at the heart of building new episodic memories. The process goes by neurogenesis, which means the birth of brand new neurons. Back in 2012, two researchers named Sheena Jocelyn and Paul Frankland laid out what we now call the neurogenic hypothesis, publishing it in the journal Learning and Memory. The core idea rewards slowing down infant brains, and this holds across humans, non-human primates, and rodents alike. Crank out new hippocampal neurons at very high rates. New neurons sound like nothing but upside, more capacity, more horsepower for learning. The catch hides in the wiring. When a fresh neuron muscles its way into an existing memory circuit, it rewires the place, replacing synaptic connections that were already busy holding information. So the exact machinery handing an infant its remarkable power to learn is, at the same moment, painting over what it just stored. The supporting evidence clicks together cleanly. A huge wave of new fibers, the mossy fibers, pushes out of a region called the dentate gyrus and into the hippocampal zone known as CA3. And that surge of fresh wiring reshapes or shoves aside the older synaptic contacts, degrading the episodic-like memories already parked there. Track the development across time, and the timing tells on itself. As the pace of neurogenesis falls off, the ability to lock in stable long-term memories rises up to meet it. High neurogenesis travels with forgetting, while lower neurogenesis travels with memories that last. 2013 delivered this trade-off in one tidy line. That new neuron formation buys extra capacity for learning at the direct expense of old memories. That mechanism cracks the forgetting wide open, and it leaves standing the single biggest question in the whole field. The one that rewrites what infantile amnesia even means. Are those early memories gone for good? Or are they still tucked in there somewhere, just past reach? Scientists carve this into two options: storage failure against retrieval failure. Storage failure says the memory never stuck in any durable way, so nothing survives to go looking for. Retrieval failure says the memory sits filed away in the brain, whole and intact, while you have simply lost the ability to haul it back up. For decades, the smart money rode on storage failure, on the notion that immature brains just do not keep these records. Fresh evidence has begun flipping that bet, and the sharpest evidence walks in on four legs, from mice. In 2018, a team that included Axel Guskulen, working inside the Jocelyn and Frankland lab, put out a study with a title that says it plainly: Recovery of Lost Infant Memories in Mice. They trained infant mice on a memory task and leaned on a technique called optogenetics, which let them tag the exact cluster of neurons that fired while the memory was forming. The tagged cluster earns the name engram, the physical fingerprint of one specific memory. Then they waited. Tested later on, the mice showed heavy forgetting, the very picture of infantile amnesia we know from people. By every outward sign, the memory had vanished. What the researchers did next is the remarkable part. Using light, they flipped those tagged engram cells straight back on. And that is when the memory returned. Reactivating the dentate gyrus engram cells kicked off recovery and lit up the downstream regions that had belonged to the original event. Nothing had been erased. The memory had waited there the entire time, silent, holding for the right key to turn. Later work pushed even further. permanently reinstating lost infantile memories by artificially updating the engram, which is what led the team to call infantile amnesia a reversible process, in mice at least. Mice were hardly the only animals telling this story. Over at New York University, Cristina Alberini and Alessio Travaglia chased the same puzzle through rats and arrived somewhere compatible. Across work published in 2016 and 2017, including a 2017 paper in the Journal of Neuroscience, they showed that latent infantile memories could be brought back to life with the right reminder. Train a rat in infancy, hand it the correct cue later on, and a robust, long-lasting memory that looked forgotten could be pulled back into the open. A catch rode along with it, and the catch matters. The 2021 follow-up revealed that recovery from infantile amnesia is developmentally constrained, so the window for reclaiming these memories does not hang open forever. Alberini and Travaglia stacked one more piece onto the picture. Infantile amnesia, they argued, reflects a critical period, a special developmental window where the hippocampus is busy learning how to learn. The infant hippocampus is not merely fumbling its memories. It is being tuned and drilled, assembling the very machinery it will lean on for the rest of that person's life. For a long time, every scrap of this evidence came from animals, which left an obvious hole. Do human infants actually encode memories in the hippocampus the way mice and rats manage to? Filling that gap meant scanning the brains of babies in the very act of forming memories, which is precisely the mountain a team at Yale set out to climb. In March of 2025, Tristan Yates and Nicholas Turk-Brown published a study in the journal Science under the title, Hippocampal Encoding of Memories in Human Infants. The obstacle jumps out the second you picture it. A baby cannot tell you a single thing about what it remembers, so the team reached for a behavioral trick, anchored in one well-established fact, that infants stare longer at whatever they recognize. Each infant met a run of pictures, objects and faces and places, one after another. Later came two pictures side by side, one already seen and one brand new, and the researchers clocked how long the baby lingered on each. Longer looking at the familiar image served as the readout for memory. All the while, fMRI recorded what the infant's brain was doing. The sample ran to 26 infants, spanning 4 months, up to nearly 25 months, split evenly between babies under 1 year and babies over it. The result came through clean. Whenever an infant later remembered an image, that same image had thrown off higher activity in the posterior hippocampus at the exact moment it first appeared. Put simply, the hippocampus was out there encoding memories, and researchers got to watch the whole thing unfold. That effect held for 11 of 13 infants past their first birthday, yet not for the ones under a year, which hints that this memory encoding ability switches on right around age 1. The Yale team pulled a careful but daring conclusion out of that. If infants are truly encoding memories in the hippocampus, then infantile amnesia might be no storage problem whatsoever. Turk-Brown framed the evidence as suggestive of more of a retrieval explanation for infant amnesia. We may carry latent, forgotten memories still sitting there in some fashion inside our brains. He added that this human work lines up remarkably well with the recent animal evidence pointing to infantile amnesia as a retrieval problem. Now this stays an open and unproven idea where humans are concerned, and the researchers themselves treat lasting adult access to these memories as a radical possibility they are still testing. The direction the evidence keeps pointing, though, is hard to ignore. So pull back and take in what we are holding. Infants form memories. The hippocampus encodes them. And the forgetting runs, at least partly, on a flood of new neurons rewiring the exact circuits meant to hold those memories. Which delivers us to the real question sitting underneath this whole video. Why would evolution assemble a brain that erases its own oldest records? What makes forgetting worth the price? The first clue is that none of this is a human quirk. Infantile amnesia surfaces across species, in humans, in non-human primates, and in rodents, every one of them an animal that runs through a long stretch of development after birth. That cross-species pattern amounts to a major tell. It means the cause almost certainly is not some uniquely human trait like language or self-awareness, but something older and more biological, wired into the maturation of the hippocampal memory system itself. That one fact quietly reshapes the popular explanations. A long-standing theory holds that we forget infancy because young children have not yet picked up language, and without language they lack the tools to encode and organize experience into the coherent narrative that autobiographical memory demands. As language skills bloom, the argument goes, so does the power to structure a memory. Something in that rings true, and language surely pulls weight in the human case. But mice and rats never acquire language, and infantile amnesia grips them all the same. So language cannot be the root cause. At most, it shapes the human edition of a far older phenomenon. This is where the adaptive framing steps forward, and it deserves to be treated as a leading theory rather than a closed case. The claim is that infantile amnesia works not as a malfunction, but as an adaptive stage in how mind and brain ripen against the pressure of the world. Sit with the trade-off the neurogenic hypothesis describes. Those new neurons scrubbing out old memories are the same new neurons handing an infant its extraordinary capacity to learn. A young brain may need to put rapid, flexible learning ahead of clinging to particular episodes, and clearing out specific memories could simply be the toll for keeping that learning wide open. Seen from that angle, the forgetting and the learning turn out to be two faces of a single process. A second adaptive idea deserves careful wording. The critical period research suggests these early years are when the hippocampus learns how to learn, constructing and calibrating the memory system a person will run for the rest of their life. Some researchers propose that the forgetting helps a developing brain work out how to hand the right weight to the right events and how to build the framework its adult memory will later ride on. The individual memories of infancy may matter far less than the tuning of the whole system, and losing them could be an ordinary step in getting that system online. Not one of these explanations counts as proven, and the honest scientists say exactly that. The adaptive reading is a reasonable take on the evidence, rather than a demonstrated fact, and the tug-of-war between the language and self-view and the biological maturation view has not been settled. What has shifted is the underlying portrait. Infantile amnesia no longer reads as a plain failure of an immature brain. It looks a great deal more like an active, structured phase of development, and possibly a necessary one, which carries us right back to where we opened. You cannot remember being a baby, and for more than 100 years that blank stretch wore the look of a defect, a limitation, or in Freud's telling, a wall of repression. The science now hands us a different story. Those years are not missing because an infant brain was too frail to record them. The memories got made, the hippocampus encoded them, and in animals at least, some of them can be found all over again. The forgetting may be the fee for a brain built to learn as fast as it possibly can, and the tuning of the very memory system you will lean on for the rest of your life. Evolution's strangest feature might be no bug in the machine. It might be part of how the machine gets built in the first place.